last time. So last time we talked about mixed phase equilibria is where we ended up. We then started talking about equilibrium concentrations. And so for mixed phase equilibria, what do I mean when I say mixed phase equilibria? Yeah, when we include gases, solids, liquids, or aqueous phase, reactants, or products. Right, so we have mixed phase, meaning that's not all the reactants or products are in the same phase. You got some in the gas phase, some in the solid phase, aqueous, and so on. And so what was kind of like the big takeaway looking at mixed phase equilibria? Clube. Does anyone remember? How do we treat solids, liquids, gases, and aqueous? What do we include and what do we exclude from the equilibrium constant? All right. Yep, that's right. So we only include gases or aqueous phases in our equilibrium constant, Kc. Right, and that had to do with if we change the concentration of a gas, right, it changes the number of moles, the volume changes, and that changes relative concentration. If we look at solids, for example, if we add more or less solid, the position of the equilibrium doesn't really change because as we go from the solid phase to the gas phase, the relative volume of that solid isn't going to change, right? It doesn't change the overall, it doesn't shift the equilibrium in one direction or the other. And same thing for liquids as well, right? So for liquids, the concentration isn't included, and we include the aqueous because the liquids, the concentration is usually so large that it doesn't play any role in shifting the equilibrium one direction or another, right? So usually water will not shift the equilibrium in one direction. Once we get into acid-base chemistry and acid and buffers as well, we'll see that the water doesn't show up. It's just the ions that show up here. All right, so that was our main takeaway from mixed phase equilibria, right? We only include the gases, and we can also define a new type of equilibrium constant, which was Kp, which is our equilibrium constant for gas phase reactions. Does anyone remember what the relationship between Kp and Kc was? Kc is usually our standard equilibrium constant. So when you see K sub C, that's your standard equilibrium constant. Does anyone remember what factors we had to consider for this relationship? Right, this was basically saying, well, we can write our equilibrium constant in terms of partial pressures of each of the gaseous species, right? Because when you think of concentration, it's the number of moles over the volume, and for a gas, we can have the pressure divided by RT. Right, so we can replace our concentrations with the pressures, and they're just related to the concentration by a factor of 1 over the temperature. So Kp was equal to Kc, and then we had this extra factor of the ideal gas constant times the temperature, and then the exponent was delta N, right? And so this tells us that the equilibrium should be shifted, or it's affected by the difference in moles between the products and the reactants, right? Delta N was what? Yep, the change in moles, right? So it was a sum, right? That's our fancy symbol for a sum of the moles of products minus the sum of the number of moles of reactants. And this is only for gaseous molecules, or gas phase. right? So that's kind of where we ended off last time. We talked about the relationship between Kp and Kc. So if we think about Kp and Kc, I guarantee if you sit and you really think about these two, you'll find there are some situations where, if Kc is large, that tells us what about the reaction? Kc is much larger than 1. What can we conclude? Yeah, it favors the products, right? And if Kp is large, we should get the same relationship. But if you find some examples, you'll see that sometimes they give opposite interpretations, right? Kc might be something around 1, and then Kp could be something much smaller than 1. And so what this means is just that these two represent the same equilibrium, but that value of 1, if you look it up, or even if you chat GPT it, it'll say, well, that value of 1 isn't invariant under this transformation, which just means that the value of 1 for Kc is not necessarily the same thing as the value of 1 for Kp, right? It represents the same equilibrium, but that value of 1 is different. So I recommend you don't think about this. I probably spent a year thinking about this and why it doesn't work out sometimes. But when we do this, we're just going between these two values. This is a equilibrium constant where the value of 1 means something different than the value of 1 for Kc. But independently, they give you the same equilibrium, right? And so this gives us a relationship between the two. We're not going to focus too much on that. This is more kind of just understanding that equilibrium can be represented in terms of the partial pressures of the gas along with the concentrations. All right, so that's where we ended with last time. Any questions on that before we continue? All right, and the very last thing that we talked about, and we introduced one problem like this, is when equilibrium concentrations are not given, they can be determined from the initial concentrations and the stoichiometric relationships in the balanced chemical equation. This is the balanced chemical equation. All right, so if we have some reaction, arbitrary reaction like this, we know that it's going to reach an equilibrium ratio. It's a dynamic equilibrium because why? Why do we call it a dynamic equilibrium? We remember that question, right, from Tuesday? A dynamic equilibrium because reactions are still happening in the forward and reverse reaction, right? But it's still equilibrium, which means what? You can say a couple things that would be correct. Okay. Yeah, that's right. The concentrations of the products and reactants are staying the same, right? So these are staying the same at equilibrium, but the reaction is still going in forward and reverse direction, right? And this is because the rates of those reactions are equal to each other. And so if we have the equilibrium constant, that tells us that we know the ratio of products and reactants with their stoichiometric coefficients included. And so we can use that to then calculate what the equilibrium concentrations should be. And we use arguments of stoichiometry, right? So here, let's say we start off with 1 molar of each species initially, right? We have initial reaction, and we know this is not going to be equilibrium, right? It's different from the ratio of these to their stoichiometric coefficients does not give us the equilibrium constant. And so what we can say is on the way, we lose a certain amount of our reactant if we know which direction the reaction is going to go. So let's say we lost 0.25 molar concentration of A. The only place that goes is to B. B, we have to say, well, if we lost 0.25 of this, we know for every A molecule, we make 2 B molecules, or for every mole of A, we get 2 moles of B. So this change is going to be twice that of A. And so then that gives us our change on the way to equilibrium. And then ultimately, just by adding up what we have in each column, we get our equilibrium concentrations, right? And the ratio of these will equal our equilibrium constant. And so everything that we do, not everything, but the vast majority of what we're going to be doing for like the next month is just setting up a table like this and understanding that the change on the way to equilibrium is related to the stoichiometric coefficients. And if we don't know these equilibrium concentrations, then we have to do this for some arbitrary change. And that's last time when we went through the example of, minus x plus x and so on. Here we're given, okay, we lose 25 molar of A. But let's say we weren't given that, we were just given the equilibrium constant. then this would have to be some arbitrary change, right? So as soon as we introduce the idea of x, it becomes more confusing, but it's the same idea. It's just we don't know what the change is sometimes. So we're saying we'll just define this as something that we don't know and we need to solve for, right? So here, we lose 25, so the problem's getting that. We lose 25 molar of A, and then we know based off of stoichiometry how that changes B, and then that gives us our equilibrium concentrations, right? And so this is an ICE table because it starts for the initial, or stands for the initial, the change, and the equilibrium values, right? And those are the 3 steps on our way to equilibrium. Okay. And so the equilibrium constant for a reaction, such as this one, if we're given a table like this, can then be calculated. So one form of asking this question is what is the equilibrium constant if you know what the change is and the initial concentration. The equilibrium constant can be calculated just by plugging in what? How would you calculate the equilibrium constant here? Right, and so this, even before we plug in any numbers or anything like that, because I don't have the numbers up here, right? What is the equilibrium constant for this reaction equal to? Hmm?
You said the equilibrium constant, that's Kc.
Yeah, Kc or Kp. We could do Kp or Kc for this one. We were given, so the reason you know to use Kp or Kc generally is because what values you're given in the problem, right? So in this problem, you're given concentration values. And you can still use concentration values even with gases. The thing with gases is you can express it either way, and both will work, right? So we're given concentration values, right? So these are all in molarities. So we'll use the concentration values for the equilibrium constant, right? What's the general expression for the equilibrium constant in terms of products and reactants? We have our concentration of products over the concentration of reactants, and each of them are raised to whatever their stoichiometric coefficient is, right? And so this can be multiple products or reactants, and they get multiplied together. And so, for this reaction specifically, A and B molecules, what is that equal to? Yep, so this would be our equilibrium constant, right? This is a ratio of B over A to a stoichiometric coefficient, and this should be constant for all initial values of the concentration. The only thing that will change that is temperature, which we haven't talked about. Right, so this is our equilibrium constant. And so if you're given something like this, where you're given the change, you would then take these equilibrium values, right? Because these concentrations are equilibrium concentrations, and just plug that into this expression. So you would get 0.5 molar squared over 0.75. And if you're asked to then find the value of the equilibrium concentration, you just divide these two. You get something like 0.33 as our equilibrium constant. And again, we don't include units, right? So kinetics, units was a huge thing, right? That was super important. What are the units of our rate constants, our proportionality constant to make sure our rates work out? Equilibrium is a little bit more complicated because these are determined in what we say are activities of the molecular species, which for chemical reactions tend to be their concentrations. So we don't include units in our equilibrium constant. And so for any reaction, the ICE table can be used to determine the equilibrium concentration of the reactants or the value of the equilibrium constant depending on what values you're given at the start and at the end. So we're going to be doing like a lot of problems through the course of equilibrium, right? So this, one of the best ways to kind of practice these or to understand this is just to do them over and over and over again. And you guys will be tired of ice tables by the time we get to thermodynamics, right? Because we're going to talk about general equilibrium, then we're going to talk about solubility equilibria, then we're going to talk about acids and bases for a little bit, and then buffers, and then we'll be done with equilibrium. All right. So here we have an example. We have 2 moles of each hydrogen gas and ion gas mixed in a 10-liter flask and allowed to come to equilibrium. And we end up with 3.5 moles of hydrogen iodide. And so we ask then, what is the value of the equilibrium constant for this reaction? Right, so the first thing we might need to do here is convert everything to concentrations. And then the second thing is going to be to make an ice table. And so generally you can probably still do things in terms of moles, but the equilibrium constant, when we solve for the equilibrium constant, that needs to be in terms of concentrations, right? So you can actually set up an ice table just in terms of the moles of the species, and sometimes it's easier to do that. But to solve for Kc, right, which is what we're solving for here, we need to have things in concentrations, right? Because Kc is expressed in terms of the concentrations. And that's what we're going to end up solving for here. And so the concentration of H2 is equal to 2 moles divided by 10 liters, should give us 0.2 molar. And then the same thing for I2 is going to be 2 moles divided by 10 liters, 0.2 molar. And then HI, we get 3.5 moles for a concentration of HI divided by 10 liters, gives us 0.35 molar, right? And what's the difference between these concentration values that we've been given? What can we identify right away? This one is actually a little bit. The products have a higher. Is that what you said?
Yeah.
Oh, I thought you said the top. Yeah. So the product, it does have a higher concentration. But what's distinct about this concentration versus these ones? When you guys rewatch the lectures, is there just a lot of like long pauses and silence? It's good. That means you guys are thinking. I don't expect you guys to answer right away. Arhelia, did you have an answer? They do. They have the same molarity. That's one thing that we noticed, right? So these two will group together, right? What's different about these two concentrations and the concentration of the product here? You.
They have a different change of molarity between H2I2 and then HI.
Yep, they do have a different value for their molarity, right? So that they, once this comes to equilibrium, their change in molarity is going to be different from the products, that's for sure. Right, so if we think about in terms of the ice table, right, and we're filling out an ice table, what's different between those concentrations?
It's an increase of 1.5 or 0.15, I guess, from reactants.
So let's think it. So you're saying it's an increase of 0.15 from these concentrations, right? So that's true. It's an increase of 0.15 for these concentrations, and for each one of these molecules, how many product molecules do we make?
2.
two, right? So there's some stoichiometry that's coming into play there. So let's see if I say how much of this is there initially?
Initially, none.
There's initially none, right? Because we start off with these two concentrations. And then what happens? What does the problem say happens?
Goes to equilibrium.
It goes to equilibrium, right? So how would we classify these two concentrations? Would I plug these into an equilibrium constant?
No, because that's the initial.
These are the initial concentrations, and this is the equilibrium concentration, right? So when we're looking at these types of problems, we have to identify what are initial concentrations and what are equilibrium concentrations going to be, right? So these are initial concentrations, and this is an equilibrium concentration. And we don't have to know exactly how we're going from initial to equilibrium yet, but it's important when we're thinking about our ice table, which is going to be, where we're initially at, our change and our equilibrium, to be able to identify these things, right? And you say, well, how do you know that these are initial concentrations? Well, it says when these two are mixed together, we think about our equilibrium mixtures from our second lab, right? Initially, you mix two things together, and then you let it come to equilibrium, right? So when these two are mixed together, that tells us that these are going to be the initial concentrations. We know that 3.5 or 0.35 molar is the equilibrium concentration because it says allowed to come to equilibrium. Right, that tells us that this is an equilibrium concentration. And they say these two are mixed. That tells us that that's an initial concentration. Right, so we're always looking for what are the kind of keywords. I was helping a friend go over his statics physics homework a week ago, and it reminded me of how many things you're supposed to interpret from the problem just based off of words that are given to you, right? So this one says it's allowed to come to equilibrium, so that one's kind of more obvious, but mixed, that's what's telling you that it's going to be initial concentrations. So if we have all this relevant information, the next thing that we're going to do is convert this into an ice table, right? So we write ice, which is I stands for what? Initial, C stands for what? And E stands for equilibrium, right? And we're going to plug in values for each of our reactants and products to then solve for the equilibrium constant, right? That's ultimately what we're trying to solve for here. And so how much HI did we start off with? What was the initial amount of hydrogen iodide here? 0, right? Because initially we're just mixing these these gases here, hydrogen gas and iodide. So that starts off at 0, right? Because initially there's no HI in the mixture. And what about for the other two?
2.
Yep, there's 2 moles.
0.2.
And you, like I said, you can do the ice tables in terms of moles, it works out. It's just when we calculate the equilibrium constant, we need to make sure that we convert it back to concentration, because the equilibrium concentration is determined, or the equilibrium constant is determined by the concentrations. So then we have 0.2, 0.2 is our 2 concentrations for each of those species. What else can we fill in here?
0.35 for change in equilibrium.
Yeah, we can fill in the equilibrium value for our product here, right? Because the problem told us that's our equilibrium concentration. So it'll be 0.35 molar is our equilibrium value from the problem. And so this is pretty much filling in everything that the problem told us. And so now we kind of have to work backwards to then fill in the rest. And what things in this ice table do we want?
Equilibrium values for all of them.
We want the equilibrium values, right? Because that allows us to solve for, right? We want to fill in the equilibrium values because that allows us to solve for Kc. Does anyone have any idea how we can fill in the rest?
Wait, just double check. The C stands for like change, right? Or
Equilibrium constant is
Oh.
for concentrations is usually what it is. So when we do Kp, it's because it's for pressures. C is for concentrations.
Oh,
So
I mean
K-
like C in the ice table.
Oh, C in the ice table stands for change, yeah, right? So initially we have some values for our concentration, equilibrium we have some values for the concentrations, and then change, that's like our change in concentration from between the two, right? So that's like our final equilibrium minus our initial kind of.
The change for HR would be plus 0.3.
We know that if this is 0.35 and we started with 0, the only change can be plus 0.35, a positive change of 0.35, right? We know that because we know how much we started with, we know how much we ended with. That tells us what the change should be for that. What do you guys think we're going to solve for or fill in next?
The changes in H and I.
Yeah, we need to know the changes in hydrogen gas and iodine gas to then get the equilibrium concentrations, right? We can't know the equilibrium constants beforehand. We need to solve for the change first before we can do that. And so how can we solve for the change? Does anyone have any idea how we can solve for the change on the way to equilibrium?
Would it just be dividing the constant, the plus constant, or the plus 35 and by 2?
Yeah, so that's exactly what it's going to end up being, right? So we know as this reaction proceeded, right, it made this much of our product, right? That means for each one of these molecules, you made how many product molecules?
2.
2, right? Because we know that from the balanced chemical equation, right? We know for each product molecule made, 1/2 reactants were used, right? So for each one of these made, we used half as much of each reactant. And so if we made this much of our products, that required a change of minus 1/2 of that for each reactant. So this will be minus 0.35 over 2 minus 0.35 over 2. And when you do that, equals 0.175, bless you, 0.7, bless you again. Minus 0.175. Right, does everyone follow why it's half of this value? So this has to do with the stoichiometry, right? So we're not even really thinking about the chemistry or the physics of the system, just on how, the amounts of reactants required to make the products allows us to make this much. And since we started with 0, we know that this exact amount of product was made, which tells us exactly how much reactants we used. And so then what do we get for our equilibrium values for H2 and I2? Yep, 0.025. Right, so all you do, you just add this value with that value, and that gives you your equilibrium value. And so if you wanted to solve for the equilibrium constant now, what would that be equal to? Mm-hmm. Yep, our HI equilibrium concentration divided by H2 concentration, I concentration, which equals 0.35 squared divided by 0.025 squared. Right, I put squared there just because these two values are the same, right? So I just combine that into one term. And when you get that, you get 196 for the value for the equilibrium constant. Bless you. And so does the value we get for our equilibrium constant somewhat correlate with our equilibrium concentrations here? Lee?
So why is there a negative sign in the change?
Because if we start with this much product, right, and we know it's used to create, so we start with this much reactants and it's used to create this much product, right? What does this change have to be? It has to be smaller, right? We have to lose we have to consume our reactants to push the reaction towards equilibrium, right? We can't create or destroy matter just because it's converted from one form or another, right? We have a conservation of mass. So if we start with 0 and we start with positive values, which we can only have positive values for these two, the only place that can go is to the products. And when we make that product, we consume what we start off with for our reactants, right? And so we'll learn also today about how to predict the direction of the change, right? Because if let's say you didn't start with equilibrium value, like a 0 right here, then it would be kind of hard to determine that, right? If we didn't start with 0 here, you would say, well, which direction is the reaction gonna go into? And we have a way to actually determine which direction the reaction will go. Wait. Mm-hmm. So does the equilibrium constant and our equilibrium values somewhat make sense with each other? If we think about the value of Kc here, right, based off the equilibrium constant, what can you conclude about the reaction? It favors the product, right? And is this what we see at our equilibrium concentrations? Yeah, we have about 10 times more of the equilibrium concentration, right? So those two make sense, right? So we always check to see, is what I'm getting making physical sense here? It also makes sense that if we start with 0 of this, that the reaction is going to move in the right direction. Okay, any questions on this problem? All right, so here's another one. We have carbon monoxide, hydrogen gas, goes to methane. And so we get a mixture at some temperature, and we have initial concentrations of carbon monoxide and hydrogen gas, right? So think about where that is in our reaction. And then it gives us, at equilibrium, the concentration is found to be 0.15 molar of one of the species. What is the value of the equilibrium constant here? Right, so again, we're asking what is the value of Kc? We're given a value, three different values for concentrations. And this here says that we have initially this much carbon monoxide and hydrogen gas here. It doesn't explicitly say anything about methane in our initial mixture, which means what? The methane is going to be 0 here. So if you guys can, right here, how do you know that this is a minus sign right here? You have to know the direction of the reaction. If you start off with 0 products, you know that the reaction is going to move in that direction, right? There's no other way for the reaction to move. As long as you don't have an equilibrium constant, or not equilibrium constant, but equilibrium constant of 0, the reaction will move towards the products. So once we have the tools to figure out which direction the reaction moves, then we can have arbitrary amounts initially, and we can determine the equilibrium constant for that. So our ice table, initial change, equilibrium. And we have each reactant and our product there. So what's our initial concentration of carbon monoxide?
0.5.
0.5 molar. H2 was 1.00 molar, and then our methanol was 0, right? And we're also given what other value?
0.15 for the final first.
Yep, 0.15 molar for our equilibrium concentration of carbon monoxide. And so these are the given values, and the red will be what we fill in. All right, so what else can we fill in from this then? Like, what's the first step?
For CO.
We can fill in the change for carbon monoxide, right? Because we know what the final was and we know what the initial was, right? So the change is just the difference between those two. And are we adding or are we subtracting?
Subtracting.
We're subtracting because we're losing reactants to make products, right? So this is gonna be minus, and what was it, 0.35?
Yeah.
0.35 molar of carbon monoxide. And so then we have to use this to then fill in everything else from the table, right? So if we lost, what are we gonna use from our chemical equation to tell us how much everything else changed?
Stoichiometry.
Stoichiometry, right? So that never goes away in chemistry. So we're gonna use stoichiometry to then determine how much H2 we also lost, right? Because it's still a reactant, bless you. And then also stoichiometry to determine how much product we actually made. All right, so what do you guys want to fill in first?
H2.
H2. So how much H2 did we make? Or lose, sorry.
0.7.
0.7 molar. Right, so how did we get that? Well, we knew for every carbon monoxide molecule we lost, every mole of carbon monoxide, we used up also 2 molecules or moles of hydrogen gas here. Right, so because our stoichiometry ratio, right, it's the same thing when we do conversions, determining limiting reactant and stuff, right? We say, well, if we use, 1 mole of this, we can convert that into how many moles of H2 we use, because for every 1 mole of this we use 2 moles of this, right? And that's the kind of conversion factors we get from our balanced chemical equation. It's the same idea here, we're just skipping a lot of the intermediate steps and just writing that this was 2 times what we lost of carbon monoxide. And what about for our product? How much of that did we make?
0.35.
0.35, right? Because for every 1 molecule of carbon monoxide that we lost, we made 1 molecule of methanol. Right, so, and then what's the sign on that gonna be?
Positive.
Positive plus, right? We're gonna be plus 0.35 molar of methanol. So now all we do, we just add and subtract these, or add these 2 lines together, and that gives us our equilibrium values. So this will be 0.3 molar of H2, and then 0.35 molar of methanol. And so our equilibrium constant is going to be equal to CH3OH over carbon monoxide H2 squared, right? So I have to include our stoichiometric coefficient. It's the only one that has a power there. And that gives us 0.35 molar squared over 0.15 times 0.3 squared. Sorry, not in the numerator, that's not squared. Plug that in. 0.35 divided by 0.15 divided by 0.3 squared. I get about 25.9. How do we feel about that so far? Thumbs up, thumbs to the side, thumbs down. Alex?
Where did you get the plus 0.35 for this CH3OH?
Because these two have a 1-to-1 ratio,
Oh,
right?
okay.
So if we have 1 mole of this consumed, that means that we made 1 mole of product. Right, so again, if this change is like, okay, where is this coming from? Think about when you're doing your limiting reactant calculations, remember how much of my product can I theoretically make versus what I actually make? And the way you did that was you used the stoichiometric coefficients to go from moles of reactants to other moles of reactants, or moles of reactants to moles of products, right? So you did a conversion that was like for every 1 mole of carbon monoxide I use, I make 1 mole of ethanol, right? And this is really, we're just counting things, right? We're not doing any super complicated physics or math here. We're just saying we're using, for every 1 mole of this, I make 1 mole of that. For every 2 moles of this, I make 1 mole of that. So that gives us a ratio of how things are made. So if I lost 0.35 moles of carbon monoxide, that means because these have a 1-to-1 ratio, I made 0.35 moles of product. If I lost 0.35 moles of carbon monoxide, that means I lost 2 times that for H2 because I need 2 of these for every 1 of these that react. Yeah, so good question. That's where those change values come from, right? These are really just our conversion factors from moles of reactants to other moles of reactants or to moles of products. All right, any other questions on that one? Okay. All right, so here's another one. We have a reaction mixture, so we'll go through this one a little bit faster. We have different stoichiometric coefficients, so be aware of that. We're given an initial concentration of methane, right? And then we're given an equilibrium concentration of 1 of the products here. And then we're also asked to solve for what are the equilibrium constants. Right, so again, we're solving for what is Kc. We're given 1 concentration at equilibrium and the initial concentration of our reactant. Okay, so I'll start filling in the ice table. So hopefully we were able to get this far. We get 0. What was it? 115. 0.115 molar of our reactant, 0. Then we had 0.035. 35 of our ethyne. Okay, so what do you guys want to fill in first? Eileen? Yeah, the ethyne molecule, right? So that we know because we start off with 0 and we ended up with that much, right? So it's kind of like tic-tac-toe with our ice board, right? You want to first fill in the first column that you can do, right? We're not allowed to go diagonal here, but we can fill in the first column at least. So that means the change is going to be what for that product? Positive 0.035. We know it's positive, 1, because it's a product and we start off with 0. Also because since we start off with 0, you know, just the math tells us that this minus that is going to be positive 0.35. So plus 0.035. And that allows us to then solve for the rest of the change values, right? And what do we use to solve for the change values? Stoichiometry, right? So the change for the reactant should be what? Positive or negative?
Negative.
Negative, right? Because we're losing reactant from where we start. We start off with this much, and the reaction moves this way, so that only goes down. The mass is converted into mass of products and reactants here. So we're gonna lose, and we're gonna lose how much of this compared to that value?
Like 0.175.
Yeah, we're gonna basically look at losing half as much as we gained of ethyne, right? So for every 1 molecule of this, we're gonna lose 2 molecules of our reactant. So that should be minus 2 times 0.035. So we get 0.07 minus. Right, so for every one molecule of these, we lose 2 molecules of our reactant. And what about for hydrogen gas? What's the sign gonna be there? Positive, right, because we're also starting from 0. And for every 1 molecule of this we make, we lose, or we gain how much? Hydrogen gas, 3 times 0.035. So that gives us 3 times 0.035, 0.105. It's positive, right? And the 3, again, comes from, bless you, the stoichiometric coefficient. And so now we have all the change values, our initial values, we can fill in the rest of the equilibrium values. So we get 0.115 minus 0.07, not divided by 0.115 minus 0.07, 0.045, and then this one is just going to be 0.105. So one thing that we can always check, that should be immediately an issue, if you ever get a negative value for any of your equilibrium values, that should signify that something went wrong, right? We added or we subtracted too much from what we started with, right? We can't create or destroy things, we can't have negative concentrations. So then our equilibrium constant is equal to what? H2 gas, power 3. Ethine to the power 1 over methane to the power of 2, right? And what values do we plug into there? This row, right? We plug in these into that. So that gives us 0.105 cubed, 0.035 over 0.045 squared. We plug all that in, 0.105 cubed divided by, or times 0.035 divided by 0.045 squared. Should get about 0.02. So again, we multiply by 2 here because we use 2 of these for every one of those. The first example we looked at, Charlie?
That one's 0, C2H2.
This one?
The initial concentration.
Because initially, here the problem says initially we contain just methane, right? So that's why we know both of the products is equal to 0. In the previous problem, or the problems, we usually had 1 on the product side and we started off with 2 different reactants. So they had to give us a mixture of those 2. But yeah, so that's why that one starts off at 0 here. Do you have a question, Julie?
For the initial concentration of the product, can we find the stoichiometry of the reactant? So
Well, no, because there's initially none,
Oh.
right? So especially so for this reaction, right? This is probably a much smaller equilibrium constant just looking at this type of reaction if I had to guess. But you can't, this is a single molecule that not decomposes, but it reacts with another molecule of itself to then make these products, right? So it probably needs to be at a very high temperature or something like that, and you're only starting off with this, which means if you only have this in the mixture, then you can't have anything else there. Okay. What we'll learn after we do one more problem and come back from a break is that if we do have a mixture of products and reactants, we can determine the direction the reaction can go, and then from there we can, if we have initial products there, then it can determine what the equilibrium constant is. As of right now though, we can't do anything if we know that there's some other reactants or products there. Make sense? Okay. All right, so let's do one more before we take a break. So here, we're gonna use an example of partial pressures and gases. So we have an example of sulfur trioxide is placed in an evacuated sealed container, meaning that you can release or add or change the pressure of the system at 600 Kelvin. And so you have this equilibrium that's established. It says the total pressure in the system at equilibrium is found to be 3 atmospheres. And the mole fraction of oxygen gas here is 0.12. And so does anyone remember what the mole fraction is? So chi O2.
Is that mole of oxygen divided by the total mole?
Yep, that's exactly right. It's the moles of oxygen divided by the total moles in the system of gas, right? So whenever you see mole fraction, that's what it's saying implicitly. So when you're given problems with gas, right, we don't necessarily have to set up an ice table because we know that the pressure of the system is going to be conserved in the total pressure, and then the pressure of the system is related to the individual pressures of each gas. So you guys might remember Dalton's law of partial pressure, right? Maybe that sounds familiar. Dalton, one of the gas guys, and that was that the total pressure is equal to the pressure of whatever the reactants and products are, right? So if we had a reaction like that, the total pressure is equal to the sum of all the partial pressures of the gas. This is again because we're assuming they're ideal gases, so one gas molecule next to another gas molecule doesn't interact any differently than if it was two same gas molecules.
Would we still use stoichiometry to solve for it?
You still use stoichiometry to solve for this, right? Because if you initially start off with all of this, right, you only have this product here, or this reactant, right? And the reaction moves in this direction. If you start off with only SO3, and you're given this much of the mole fraction of O2, how much mole fraction do you think there is of SO2?
Like 240?
Yeah, it should be twice that amount, right? So this will be twice that amount, because if we only start off, so again, we're using the idea again that initially we start off with 0 of our products. So that tells us, because we start off with 0, that whatever we make of this is related stoichiometrically to our other product here, right? And so we're gonna have to think, okay, if the total pressures have to add up here, right? The total pressures, so if I P total is equal to P SO2 plus P O2 plus P SO3, right? This one, we know the problem gives us. We know then this one, because it's related to the stoichiometry of this mole fraction. And then this is the one that we don't know yet, right? So we have to find the partial pressure of SO3 here. That's the only one that we don't have to find. And what are we asked to find? Well, eventually we're asked to find Kp for the system, right? So we have to think about what is Kp equal to. We're given everything in terms of pressure here, so this is actually one of the times that we just use the pressures in our equilibrium constant. Right, so how is the mole fraction related to the partial pressure of a gas? Well, the partial pressure of A, for example, is the mole fraction of A times the total pressure. Right, so these are the expressions that go into a sum like this. Right, and this is basically saying, well, if the partial pressures of each of the gases can be separated and we just add them up, then if we know the percentage of the gas that's one species or not, the total pressure times that percentage just gives us the amount there. Right, the fraction of A times the total pressure tells us what portion of the total pressure is due to species A, or whatever molecular species A is. And so PO2 is then equal to what? PO2 should be equal to 0.36, right? Because we have P total times the mole fraction of O2, which is 0.12. So that'll be 3 atmospheres times 0.12, which equals 0.36 ATM. And then PO2 and PSO2 are related because for every molecule of O2 we create how many SO2s? 2, right? Because of the stoichiometric coefficient, right? So this tells us 2 SO2 gas molecules per O2 gas molecule. Right, so if we think about like how what the system is actually doing physically, right, as this reaction proceeds, right, we're making 1 mole of this, which is changing the pressure because we're adding oxygen to the system, and then for every 1 mole of oxygen gas that changes the pressure, we have 2 moles of our other product that's also changing the pressure, right? So we're going from something that's starting with 2 moles of gas, and we're creating 3 moles of gas. Right, so the pressure should be increasing as the system moves towards equilibrium. Right, we're creating more moles of gas. We're using 2 and we're making 3. Right, and the pressure is directly related to the sum of all of them. So if those 2 are related, by that means that the mole fraction of SO2 is equal to 2 times the mole fraction of O2. And that tells us that PSO2 is equal to 2 times the partial pressure of O2. Right, so if I just plug in 2 times 0.24 there, that's the same thing as just multiplying this whole thing by 2. So that means that it's PSO2 equals 0.72 atmospheres. So those are our 2 partial pressures. And we need all of them to solve for Kp, right? Because Kp is equal to what? For this reaction. What's Kp equal to? It's the ratio of what for gases? It's the same thing as for concentrations, except we put the pressures in instead of, right? So it'll be PSO2, PO2 squared over PSO3 squared. Right, so it's the exact same thing as our equilibrium constant for concentrations, except just in terms of the pressures. right? So this is what we want to plug everything into. That's why we need all the individual partial pressures of the gas. If we were just asking to solve for the partial pressure of our reactant at equilibrium, we could just stop there. But here we're going to be plugging that into Kp. Further?
How do we know what the partial pressure for SO3 is?
Because now we're going to do that, that's the next step, right? So if we know, right, so now think about this expression right here. What do we know here?
SO2 and O2.
And what else?
And
The total pressure, right? So if we know this, that, and this, then all we have to do is we just solve for SO3. Sorry, I was pointing at the wrong one. We know this, this, and this, and we need to solve for that one. Right? Because that relationship for the total pressures is this, that stays the same. This is saying that all of the partial pressures of each gas add up to 3 atmospheres. So we can use that. On the next page, we have P total minus P SO2 minus PO2 equals PSO3. So that's 3 atmosphere minus 0.36 minus 0.72 atmospheres. That gives us 3, bless you, 0.36 minus 0.72. 1.92 atmospheres equals PSO3. And then Kp is equal to 0.36, 0.72 squared over 1.92 squared times 0.72 squared divided by 1.92 squared. So I get 0.050. Okay, any questions on that? All right, and then in the future, we'll use partial pressures, and you can use them with ice tables. You just have to know the partial pressures before a reaction starts. So this question, we couldn't do that because it gave us the total final pressure. We would have to know at least the total initial pressure to do that. We'll go over that when we get to it. All right, so let's take a 13-minute break. So we'll be back at about 10. I guess the clock's a little different. We'll be back at 10, and then we'll finish up part 2 of equilibrium, and we'll talk about which reaction quotients and which directions equilibrium can move.
Or stoichiometry is possible only on one
Right,
side
because
of
if we
the
hit
weight.
24.12 plus 0.24 minus 1, so 0.64, 0.64 times 3, you get 1.92, and that's what we got.
No.
Yep, you get the same pressure for all 3 of them if you do it that way as well. Right, 0.192 is the same total partial pressure of the gas.
Oh, okay.
But I did that. I did that knowing. Actually, no. I used the fact that this one is 0.24 of the total mole fraction to get the total.
But yeah, I
So like you're saying, how would you, right? So the pressure of the mole fraction of SO3 isn't necessarily 2 times 0.12.
Like try to like understand it before going to class.
Does that make sense? Here, let me pause this. And let's go ahead and continue. All right, so now you guys had 15 minutes to think about this. Anyone have any other questions about this, or any questions come up? No. All right. All right. So now we're going to go into predicting the direction of change. All right. So this is the last part of equilibrium, part 2. So if we have a different initial mixture, how can we determine the direction that equilibrium is going to move? Like, let's say we don't have 0 products at the beginning. How do we know which direction is going to, which direction the reaction is going to move? And so this is going to be related to something called the reaction quotient, right? And the reaction quotient is going to be exactly the same if we have a reaction A to A plus B to B, C to D, C plus D to D. It's going to be exactly the same as the equilibrium constant, except the values of these concentrations represent something different. Right, and so when we're looking at an equilibrium constant, the amount of products or reactants in a reaction mixture depends on the value of that equilibrium constant, right? So we said that if a equilibrium constant is much larger than 1, what's favored? The products, and if it's much smaller than 1, the reactant, right? The opposite. And so the reaction quotient takes that idea and just applies it to non-equilibrium concentrations. And so the values that are used in the reaction quotient are just the concentrations that are not going to be at equilibrium constant. So again, QC for this reaction, you guys don't have to write this again, is going to be CC, DD, A, and B, right? Except these are not equilibrium concentrations. And so the reaction quotient on its own isn't really going to tell us much, right? Because equilibrium tells us, what is the ratio of products to concentrations at the point at which those concentrations are not changing anymore. The reaction quotient, right, if we're still not at equilibrium, we don't really understand that system unless we're looking at kinetics, right? Because things are still moving around. So that doesn't really tell us anything about, equilibrium properties of the system, because things are still moving around. And so what we're going to have to do is we're going to have to compare the value of the reaction quotient to the equilibrium constant. And we're keeping in mind the general trends that we have for the equilibrium constant. And that'll tell us how the reaction should proceed in these cases. And so the value of Q relative to Kc is a measure of the progress of the reaction towards equilibrium, right? So if we compare these two values, we're saying how far from equilibrium are we, and based off of the relative magnitude, or is it larger or smaller, that'll tell us which direction the reaction is going to move. And so at equilibrium, those two should be what to each other? Equilibrium constant and Q. What do you guys think? Right, if the form of Q is this right here, at equilibrium, what do you think? How do you think Q and K are going to be related? Right, so it's a measure of the reaction progress. So once you reach equilibrium, how do you think Q will be different than K?
No.
No, because these concentrations that you plug in once you reach equilibrium are the same as the equilibrium concentrations, right? So those two are going to be equal to each other at equilibrium. And so, if we were to compare, actually I'll do that in a little bit. And so we have a chart here where we have different initial concentrations that give us different ratios. So that gives us different values of Q. So it's a function of the initial concentrations of A or B in a mixture, and we compare them to the equilibrium constant. So if we take some values, be like 0.55, if that was the equilibrium constant, you would say that the reactants are favored, right? Because it's something that's less than 1. But it's not at equilibrium, so we can't really analyze that like an equilibrium constant. What we can say though is that this value compared to that value is smaller, right? Which means that at equilibrium, the products should be larger than what we have in this current mixture, right? So the products are larger here than what we have in our current mixture, which means the reaction needs to move towards the direction of the products. Here, we see that the value is larger, which means that the ratio of the products to the reactants is larger, which means we have more products in this mixture right here than we do at equilibrium, right? The equilibrium is the same for any initial mixture of concentrations, right? Because we always reach that equilibrium state where concentrations are changing. And this ratio stays the same. So the initial ratio is larger than that of the equilibrium ratio, which means that this has more products than the equilibrium mixture. So to reach that equilibrium ratio, we move to the left. We move away from the products to kind of balance out the ratio to reach the equilibrium mixture. And then when they're equal to each other, that's when we've reached equilibrium, right? So if those two things are equal to each other, that means we do have an equilibrium mixture there. The reaction is not going to move in one direction or the other. Reaction is still happening back and forth, but the concentrations aren't changing anymore. Right, so how do we compare these? Well, again, the reaction quotient is relative to equilibrium constant is a measure of the reaction, of the progress of the reaction towards equilibrium. And so if Q is greater than Kc, that means that, and I'll just do for a simple reaction, A to B, because I don't want to write all the other letters. That means that B over A, write this a little smaller, B over A, and I'll put NE for not equilibrium, is greater than B over A for equilibrium. So this is, now with this expression on the board, we can say what we were saying in words a little bit more, hopefully highlight that a little bit better. Here, let me put equilibrium for both of these here. So we're saying that this ratio is larger than the equilibrium ratio, which means that there's too much B relative to A in our mixture. So to make the reaction reach equilibrium, that means we need to take some of the B and convert it to A to make this number get smaller until it reaches the equilibrium ratio. Right, so this, we have to go kind of downward to make B turn into A, to then make these values the same. Right now, when this is larger, it's saying that we have too much B relative to A. So that means that this is going to shift towards the reactants. Right, we have too much product here, it's going to shift towards the reactants. If we have not equilibrium not equilibrium, is less than the equilibrium ratios. Now we're saying that this value is smaller than that, which means that we have too much A relative to B in our mixture. So the reaction is going to have to shift to make more products to then reach the equilibrium ratio. So this is going to shift towards the products. And then when they're equal to each other, that means that there's not going to be any change. No reaction movement, because we're saying, okay, well, this ratio is already equal to each other, so we're not going to have to make any or use up any products. Make any products or use up any reactants or vice versa. Right, so a lot of people, they'll ascribe those to memory. But if you don't remember exactly which way it goes, you can always just write down a simple reaction like this and say, well, this is larger than the equilibrium ratio. How can I change these concentrations to reach whatever this ratio is supposed to be, right? So when it's larger, that means we have too much product. I need to make reactants. So this tells us which direction the reaction will proceed. So when we're looking at our ice tables now, if we have some initial concentrations of both products and reactants, this says which way is the reaction going to proceed. If we know which way it's going to proceed, then we can do an ice table without just 0 as our initial values. All right, so let's look at an example of this here. So here we have some mixture of concentrations of our reactants and products here, and we're given the equilibrium constant. And so we ask, is it at equilibrium? So to determine if it's at equilibrium, what do we need to do? How do we determine if the system is at equilibrium here?
Find the reaction quotient.
Yeah, we need to find the reaction quotient, right? So we need to calculate QC. And then once we have the reaction quotient, the next question asks, if we're not at equilibrium, which direction will the reaction proceed? How do we determine which direction the reaction is going to proceed? Right? Is it going to go this way or that way? Then we're going to compare it to the equilibrium value, right? So we're going to compare QC to KC. And once you compare those, then that tells you, okay, how far am I from equilibrium? In which way do I need to move to establish equilibrium again? All right, so is it at equilibrium? Let's calculate QC. QC is going to equal to the concentration of H2 to the 4th power, CS2, I'm sorry, there's a typo there, so it's overlapped, over CH4 and H2S to the 2nd power. So we plug in these values, 1.12 molars squared, 1.43, sorry, to the 4th power, 1.32 squared times 1.26. So 1.12 to the 4th power times 1.43 divided by 1.32 squared divided by 1.26. 1.02 as our reaction quotient. Right, so is the mixture at equilibrium? No, right, because Kc was the thing 3.59? 3.59. Right, so this is not at equilibrium. And so what do? We compare QC to KC, question mark, right? And we see that QC is less than KC. Right, so if QC is less than KC, the reaction is going to shift which way? To the products, right? Because this ratio, right, we're saying that we have too much reactants relative to the products, which means we need to shift towards the products to balance out the ratio, right? So we're going to shift right. Okay. Any questions on it? And so kind of a way you can also remember this is comparing QC to KC, is that if you put KC on the left and QC on the right, the arrow points in the direction of the reaction. Right, so if we put KC is less than QC, the reaction shifts left. And then KC greater than QC, the reaction shifts right. Right, so if we look at the direction of the greater or equal than sign, it tells you if you put it in this order, which direction the reaction is going to shift. So if you want a quick way to do that, you just always put KC on the left. All right, any questions on the reaction quotient? All right, so the reaction quotient is saying how far are we from equilibrium, and when we compare it with our equilibrium constant, it tells us which direction are we going to move to then reach equilibrium.